You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health podcast, and I have Yong Lin Kong. He's at the University of Utah College of Engineering, and we're going to be talking about his work there. So, Yong, thanks for coming. How you doing?
Good. Thank you so much for having me here, Rich. I'm really excited with this invitation.
Yeah, I know it's not all you're doing, but I saw an article from MIT News that you're working on 3D printing of ingestible wireless biomedical electronics, an ingestible capsule that can be controlled wirelessly. But in addition to that, is there other work that you're doing? And, we'll kind of talk about that and maybe other stuff.
Yes. So the 3D printed ingestible electronics is one of the example of potential applications of the technology we are developing. I'm an assistant professor at the mechanical engineering department in the University of Utah. And my research focuses on the development of novel additive manufacturing technologies to create unique, functional, interwoven architectures and devices that cannot be created with conventional fabrication methods. The multi-scale, multi-materials 3D printing approach, we believe, can overcome the geometrical, mechanical, and material dichotomies between conventional manufacturing technologies and a broad range of three-dimensional systems. And ultimately, our goal is to address unmet clinical needs with the ability to create tailorable three-dimensional freeform hybrid biomedical devices with this technology. And the ingestible electronics is one of the examples of what we can create by developing the 3D printing technology.
As you're talking about it, there's two things. There's 3D printing versus manufacturing something to be swallowed. So right now we manufacture pills all the time, essentially they're not really 3D printed. So I guess you can 3D print a pill, or you can 3D print or manufacture something else that could be swallowed that would do different things in the body. So maybe let's start with 3D printing versus non-3D printing. What kinds of ingestibles have you conceived or are looking at? And then we'll go to the functionality part of it.
I see. So Rich, just to clarify your question was on what is the difference between using a 3D printing to create a pill versus using conventional manufacturing technology. Is that right?
Right. And then after that is, what else can you, because of 3D printing, what can you create that can be ingested that we can't create right now? But, maybe first thing is 3D printing pills versus just manufacturing pills. Is there any benefit there?
Yes. Because our body is very different between individuals and individuals. Personalizations of biomedical devices is something of significant interest. For example, in terms of ingestible pills, in this case, what we demonstrated is the ability to prolong the gastric residence of the device in the stomach, which conventionally is extremely challenging with the manufacturing processes that we have. This is challenging because our stomach is an inherently hostile environment. So we have to design a device that has various integrated functionalities, but at the same time can sustain and inside the hostile gastric environment have the robustness that is needed. At the same time, is in a form factor that can be ingested. So conventional manufacturing technology is challenging to achieve that because, for example, electronics is typically rigid and planar processes. In this case, it is challenging to integrate it directly with without a three-dimensional fabrication approach.
So what are some of the differences in people that make some pills not work and some pills work? Is it that in some people they have very quick gastric emptying and the pill just doesn't stay long enough? Or is it in some people the gastric emptying is too slow and the pill sits there for too long and it gives them too much medication? What are the differences that cause challenges in swallowing pills?
Yes, I think both are really good points. One is the gastric residence periods that could vary between people, but at the same time, it is also something that could vary depending on the applications that we want to administer, the applications of the ingestible electronics. Second thing is the dosage of the drugs. That is something, again, different target applications and drugs that target different diseases have significantly different dosage and require significantly different design of the device.
So what are some design changes that would accommodate different dosages or on-demand dosing, let's say?
So the design changes, that there are two design changes that need to be tailored. First is for the purpose of gastric residence. For the purpose of gastric residence, the way we achieve the gastric residence is by using multi-material 3D printing to create hybrid structures that contains the flexible and the biocompatible rigid components. And the way the device stays in the stomach is through basically a transformable architecture that can be folded into a shape of a capsule. And upon ingestion in the stomach, the capsule will dissolve, which allows the device to expand into a dimension that is larger than the exit of the stomach, which is the pylorus. So the ability to stay in the stomach depends on the robustness of this architecture, and hence by changing this gastric residence architectures, for example, using 3D printer by modulating the composite design, we basically will be tailoring and tuning the gastric residence period of that structures in the stomach. So this is for the gastric residence aspect. The other aspect is for the dosage. That depends on, for example, the drug reservoir that we can integrate in the ingestible device, and also the control release formulations that can be custom formulated to adjust the release of drugs in the system.
Well, it sounds somewhat problematic if you have a device that can unfold once it's in the stomach, unless that could be controlled from the outside and probably with the assist of a camera. What if it unfolds and the person is not reacting well to the drug and you need to fold it back up and get it out of there? How do you do that? So it seems like you need control to do that, wirelessly. And then I don't even know if you could integrate a camera, but what if the way it unfolds because of the morphology of the stomach is a problem, or if it unfolds in the wrong spot? Maybe someone has some acid reflux and the pill senses that before it reaches the stomach and unfolds in the sphincter and causes the person a problem. I don't know.
Yeah, that's a great question, Rich. In fact, that is one of our current focus is to design triggerable release system, which can be achieved with different approach. For example, we can design an electroactive adhesive so that in the event that we need to release the device from the stomach, we can wirelessly communicate to release the structures. So what we have shown in this published work is the ability to stay inside the stomach, and through passive disintegrations, it could ultimately break down into smaller pieces and pass from the stomach. But as you said, an approach that can actively trigger the disintegrations of the device could be important in terms of safety in some applications. So, for example, there is a drug allergy. So our focus now is to design a triggerable release system, which we have also shown some preliminary results by using electroactive adhesive, which ultimately could overcome this safety concern.
Yeah, once a particular pill delivers its payload, you'd want it to dissolve and go away and be passed through the system. You don't want it sitting there, because how could you take more than one? The material could build up and build up and cause all kinds of obstruction and problems.
Yes. So there's several interesting things I learned throughout this project. Is stomach is a large organ that can tolerate a lot of foreign objects and materials. In fact, it is one of the few organs that has been evolved to tolerate foreign materials such as the food, the breakfast I had just now. It is relatively immune privileged. So the depositions of objects in the stomach is relatively harmless in comparison to, say, the implantations of device in other organs. But as you said, we also do not want situations where you have too many foreign objects staying in the stomach for a long period of time. In fact, there are some medical conditions where the patients keep eating hairs, and that causes accumulations of hairs inside the stomach. So having the ability to ensure the disintegration of the device from the stomach, in this case, we show true passive disintegration is important. And we have shown that over a maximum of 30 days period, the device will naturally pass from the stomach to outside the body. But as discussed, what we are focusing now is to develop an active triggering system where we can remove on demand the structures from the stomach.
How would you remove it on demand? What's an example of that?
So this is one of the future works. In this case, we synthesize conductive polymers that has a strong adhesion property. And these polymers can be used to bind the structures that basically impart the gastric residence property. Through electrical triggering, we can then causes, for example, jaw heating that causes the material to lose its adhesive property, allowing the basically disintegrations of the device of the structures, which then remove the gastric residence property. So this is one potential applications, potential strategies. The other strategies is, for example, using shape memory polymers and other transformable architectures that allows the transformations between ingestible dosage form and a gastric residence dosage format.
Okay, very interesting. So how far are you in the development? What has been accomplished, and how long until this is testable in animals or in people?
So in terms of ingestible electronics, what we have shown in this is the ability to stay in the stomach. One of the focus now is to look into how to trigger the disintegrations, and the other focus is to how to control such a system using external field, such as magnetic field. In fact, we recently just received a $2 million funding from NSF to develop a 3D printing approach that can integrate multiple different functional materials into the 3D printing process. For example, integrating magnetic functionalities, which in the future we hope can use magnetic field to control the motions of the ingested device for various different applications. So we are at the proof of concept stage in this approach, where we develop different manufacturing approach and technology.
Well, very good. Is this going to affect other implants in the body, or is it plenty to just focus on the digestible ones?
So broadly, we are developing different biomedical devices. This is just one of the examples where we can impart electronic functionalities into an ingestible gastric residence system. We are looking into, for example, using the 3D printable electronics approach to integrate electronic functionalities into various prosthetics, regeneration implant, which could have the same impact of that, which could impart functionality which otherwise remains inachievable with current manufacturing technologies.
Would it be possible for an ingested pill to go through the bladder part of it and part of it go through the colon? Could you split up the functionality so that it goes one way or another, or both ways?
So for Yes, so we can for colon. Yes, I think for bladder that would be uh, uh because it's in a different organ, so it's not in the GI tract. So, but for other parts of the GI tract, such as the colon or intestine, that's something that we can customize the gastric residence architecture so that it stays at that locations rather at those locations rather than in the stomach. So there are several pros and cons in different locations. For example, in the stomach, it is relatively immune privileged, so it can handle the device residence for extended period of time. But in intestine, in contrast, it could allow a more rapid delivery of drugs directly into a system, into the body. So that's a great question where different locations of the body could have different potential applications, and we certainly could use 3D printing to design customized gastric residence structures, to stay at the different location.
Yeah, you could have part of the payload stop in the stomach and the rest of it stop in the intestine or the colon, etc. So you could do multiple different destinations, I guess.
Yes, and is a good point because those different application destinations will have different potential applications that can address different unmet clinical needs.
It'd be like a medical cruise ship. The first stop is the stomach, and the second stop's the intestine, and the third stop's the colon.
Yeah, yes, that would be really cool. Yes. The thing I want to point out is that this it involves different engineering of, for example, materials that is compatible with different environments. But with this material engineering, we can achieve such gastric residence or residence at different components, different part of the body.
How do you ensure that something will be deployed in the stomach versus the intestine or the colon?
Yeah, that's a great question. So in fact, this is one of the safety concerns with this technology. But we can achieve this by basically ensuring that by timing the capsule so that it dissolves within a certain time period, that and ensure that the expansions of the device happen quickly upon exposure to gastric fluids. So that's the first preliminary prerequisite of achieving this work, which we have shown in the early part of the paper, where the structures will rapidly expand in the stomach.
Well, I would think the chemical nature of the stomach environment versus the intestine versus the colon is probably very different, which would make it easier.
Yes. And that is a really good point because one of the future work is to integrate enteric polymer, which is a polymer that would dissolve in one of the environment, so that in the event that the structures get passed to the intestine, that the polymer will disintegrate because of the difference in the pH in the environment.
Well, beyond pH, I'm sure there's other chemical elements that you can identify that are unique to the intestine or the stomach, right?
Yes. Primarily, the pH is significantly different, but there are differences in terms of huge differences in terms of chemical environment.
Okay, and then the transmission, the wireless transmission, if it's inside the stomach, is there much barrier to a signal getting out or getting in, or is it the body pretty, conductive where nothing, the signals can get out or get in?
So yes, that is one of the focus of the research as well, because for low frequency, the body can basically the signals can get past the body pretty easily. But at higher frequency, the signals get attenuated. And what we have shown is the ability to transmit Bluetooth signals, which is at 2.4 gigahertz. And the reason why we want to achieve that is because this allows us to directly communicate with smart devices such as smartphones and tablets. And at the same time, the attenuation is something attractive in this perspective, because if we have, say, ingestible gastric resident electronics in our body, we certainly do not want anyone in the same room or outside our neighbors to be able to pull out the smartphone and connect to our device. So what we have done is to tune the transmission range so that it is within the arm's length of the person. So in other words, we have physical isolation from the transmissions of the device, so that it is isolated to that person.
Oh, because you're worried about what people being, someone trying to assassinate somebody or to mess with their medication and hurt them?
That is one potential security concern, as I think this is something that could potentially be an important topic that we need to address in the future if this is translated in the clinical settings. But having a transmission that self-limits within the patient or the user provides an additional security in comparison to having transmit the signals to the entire room or to a wide area.
I guess you'd have to do things like what bank does is, banks do. The password would have to change maybe every time you want to access it. Like every minute the password would change. They have that with some bank accounts. And, if the pill only stays resident in a max of 30 days, that would help as well. But, proximity is one thing. But if someone hacked someone's smartphone and they had it on them, they could access the pill if it wasn't protected properly,
Yes, I agree. So having a limitations in the range, so allows us to focus the security development on the smartphone. Otherwise, there's two different methods this can be hacked. In other words, if the range is too big, then anyone with a Bluetooth device could potentially try to bypass the security to control the device. So having a limited range allows us to focus our security enhancements on the smartphone or devices that is connected to the device. Or to be safe, the device can always remain disconnected with the smartphone unless it is needed. So that is another way to increase the security of the device.
Sure. Okay. Well, very good. So what's your goal for the next year or a couple of years? What do you have on your roadmap? What do you want to accomplish?
Yeah. So one of the things is focusing on improving the ability to control, for example, the motions of the locations and the operations of the device when it is inside the stomach. As mentioned earlier, this is funded through NSF, where we will impart magnetic components to allow us to use magnetic fields to control the locations of the device. So this is something that we are working on currently. So in other words, it's no longer a passive ingested pill, but more like a soft robot that can hopefully traverse inside the human body for different applications.
And what's the best way for people to get in touch and ask more questions?
So they could reach me to my email, yong.kong@utah.edu, or they could also visit the website of the group. And I'm very excited with potential collaborations for anyone who is listening, and to extend these applications to different to address different unmet clinical needs. And I look forward to work with everyone who is interested to do 3D printing research in the highly 3D-dimensional environment at the University of Utah.
Well, very good, Yong. Thanks for coming on the podcast. I appreciate it.
No, thank you so much for your time, Rich. I really enjoyed the conversation.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.